Alright, hell yeah. So what we're going to do is integrate area. So we're going to do a lot of double integration, and we're going to do a fairly simple shape. So hell yeah. In the engineering books, there is a lot of just this symbol. Hey, you have an integral sign. They won't even specify a region, but you could say, hey, it's just the region of that area. You know what I mean? Sometimes this is an R. I just watched a video. They're like, hell yeah, R for region. So you're going to integrate over that region a small element. And so you draw a square and call it dA. So that's a small little chunk of area. And in general, you could take that small square and then grid this whole little bean shape and then count up the little squares. Okay, but the only tricky thing or weird thing with integration is that this really isn't even, it's a square, but it just gets so small that it gets infinitesimally small. And so that's what drives me nuts, and that I'll even mention it with the double integral, because if we do have an integral, hell yeah, you know what I mean? You're going to maybe make a little width here and then integrate along those limits, and then take that slice and then integrate along that limit. Or take this little width here and then integrate along these limits to get that slice, and then take that slice and add up all the slices. But when you get that first slice, you know, whether it's vertical or horizontal, that doesn't have area. And that's what's driving me mad even for this video. It's just like, darn it, man. Because that still is an infinitesimally narrow strip that still doesn't have area. So going back to this little chunk, this little square dA, like, what does this have? Well, not only does it not have area, it doesn't even have dimension. It doesn't even have length. At least when you do that first integral and you get a little strip, you know what I mean? If you say that this has like a dimension right here of dy, that's so infinitesimally small, but hey, at least it has length. So you take something, this little square dA, which you think is area, but actually is just a microscopic point that, you know, is infinitesimally small. And so it doesn't have dimension. You integrate the first time, you get length, cool, you get this, and then you integrate the second time, and then you get, you know, your area. So, alright, so that's a pretty good introduction. Especially because I was all excited, because doing the double integral, you're like, hell yeah, I integrate the first time, and look at that little strip of area that I get. You know what I mean? But it's not necessarily an area, and it might be better for me to nip that right now and be like, no, that's a length. Because a lot of problems you can use that concept of like, hey, if I have this little dx and I'm integrating along like this little you know, x value from x to whatever, hell yeah, I get a length. And that might be more useful to think of it as a length instead of thinking of it as a little area with with infinitesimally small like height, width but no height. All right, so it's a length. All right, let's do it. But I still maybe am going to think like, hey, I still got some area. I'm still going to visualize that, nah, I got some area. Look at that, that's area. But then I'm going to also go back and try to tell myself, nah, that's a length. Okay, but let's do it. So for this problem, we're going to put three little dAs, you know, little squares. So I'm going to put a square right here, I'm going to put a square right here, and then put a square right here. Sweet. So these all have dAs. They're all, you know, little area dA. I'm going to call this one dA1, dA2, and then dA3. And in general, what we're trying to find is like, hey, we're going to say this area right in here is area 1, this area right in 2 is area 2, and this is area 3. And with the little, and I kind of messed up my picture, we got more though. I could do this. This is really important for calculus, is actually get that little width in there and call it d. So in this direction it's dy, little change in y. This direction is a little change in x. And you know, they have this x value going to the center, but if it's infinitesimally small, it doesn't matter if you go to the edge or, you know what I mean? So this distance to this edge right there is the same as maybe going to the center. Or maybe I don't actually draw that in right, because when I do my integrations, I put this little dx right there and do the x value up to that. But as this shrinks down, this dimension is no different than the center than to this outside edge, because it goes infinitesimally small. But I don't know. I'll have to look at some books. Is it useful to put that x value and then the dx like that, with the x going to the center? I don't think so. But, alright, with that said, so we're going to do that to our drawing. We're going to come down here with our little dx's, and we can take them all the way to the ceiling. And then same thing this direction. We're going to do our little dy's. So we got dy, and then we have this value of y up to that little dy, and then over here we have this value x to there. I'm going to call this y1, and this is going to be x1. So again, even right here it's kind of small. I have a dx, and then I have an x value to that. So for this one it's x1, and sure, it could be dx1, but whatever, and dy1. Okay, so for these, same thing. I'm going to have a dx2, this one, a dx3, and we're going to have a dy3. Cool. And right here, dy2. Alright, sweet. So now we're going to set up our integration. And so, you know, it's like a double integral. Well, you'd have area is equal to the integral of dA. So that's what we have, and we have that region. And so we're going to say, hey, that's the double integral of... Now, I labeled this dx and dy, so, you know, on another sheet of paper, I can say that the dimension of this thing is dx dy. And if this area is dA, I can say that dA is just dx dy. You know what I mean? That's that area. That's the area of that small little square. Alright, sweet. So, when I know the area, well, what are we doing? Okay, so we're going to, yeah, so this dA, I can substitute that dx dy. And the whole point is to add up these squares. Now, I could just, and I think that's like, what am I going to do? Am I going to start adding that one and then go this way and then go that way? You know what I mean? I guess that people don't talk about is like, well, there's got to be a rhyme and reason of adding them. So might as well add them vertically first, you know what I mean, like that, or horizontal, or add them horizontally. So I'm going to add that one, you know, add those up. And then once I add those up, then I can use that as a slice, and that's more familiar, you know, with when integrating. But yeah, the reason I'm making these videos is sometimes that little box isn't very intuitive. You're like, what do I do with it? You know, if I had a slice, I know what to do with that. And, I mean, you can even, I guess why I'm making this is because, hey, this term comes up a lot in engineering. And it's just, sometimes it's hard to see that it is a double integral when it's like, I don't even know if I would want to set up a double integral. Why would you? You know, the whole idea is just like, well, just take a slice right here. The slice has a height of equal to h, so I can even say, hey, this is an equation right here. This equation is y is equal to h. This is an equation right here, y is equal to 0. And then if I had this as my whole slice, then I would just integrate from 0 in the x direction, if that's a dx. I would just integrate from 0 to, I'm just going to say this thickness is t. I'm going to say all around this thickness is t. So that's going to be for this video. But yeah, so it's just like, why would you even do a double integral? It doesn't seem necessary. Alright, hell yeah. And just right there, that was the aha moment of like, well, if you actually had a line, well, how did you get a line? The only way to get a line was to take, you know, like I said, this was an equation and this was an equation. But in doing that, I already found a height. And a height is a line. You know what I mean? Back to this dA, this is an infinitesimal point. It has no dimension. And so, so the fact that I can just skip over the double integral and say, well, why do I know this height? You know what I mean? Why am I just so confident that I could figure out this slice? Is because I know equations, and I can see this is an equation for, you know, just a constant value of h. This is an equation for a constant value of y. Integration is the idea of you know, finding the area below a curve and you know, in between two lines. Or, I guess, setting, if this value is 0, hell yeah, integration is just taking that equation and finding the area from that equation down to the x-axis or something like that. It'd be the area under that curve. But yeah, the area under the curve only to the neutral axis. You know what I mean? That's the idea of integration. But yeah, so heck yeah. So what you did in that, you know, just by looking at this and making a slice, you just already intuited that first integral. So let's do that. So if we already, and we're gonna figure out that. So the first one, we need the boxes this way, and so if we're doing the boxes this way, we're gonna take that dx slice and oh, yeah, I've been making a few videos on this, and maybe I have been messing up. Yeah. No. Yeah, see, it's just like, I'm so in, yeah, this is where I mess up. It's just like, well, I'm going to take this dx slice and then integrate this direction. And it's like, no, you're not. You're not going to see your error until the next integration. Because once I get that slice, then what are you going to do? You're going to take a dy slice, and then what, go this way? Well, you know what I mean? So your dx slice, if I slice it along this x-axis, I got my limits have to be this way. So if I'm taking this square and I'm going to take this dx, I have to add it this way. But I just said that I want to add it vertically. You know what I mean? But it wasn't intuitive for me to see that, no, then I need to take this dy, you know, little chunk. So I'm going to take that little width of dy, and then I'm going to add them up from along this y-axis this way. So hell yeah. So I'm going to switch this around. So the first integral I'm going to do is dy, and then I'm going to do the dx. So I'm going to take this little dy, and we're going to go from the integral of y equals 0. So we got y is equal to 0 to y is equal to h. Hell yeah. And then once I get that strip, then I'm going to add up all of them. Then I'll have that strip. And might as well just do that first. But once I get that strip, it'll have a height of h. So that's what we should be seeing here in a second. And then I'm going to say the area of that strip. So now I might call that, so how I called this box dA1, I'm going to call the area of this strip dA1 prime. Because that's where I, you know, this is kind of like my first rodeo today doing these videos on double integrals and areas, so bear with me. But it's fascinating because this is where I ran into, like, my biggest headache. I was just like, well, isn't this little square a small little chunk of area? And after I integrate a first time, like, you know what I mean? Don't I get area? And it's like, nah, not really. You get length, and this little square that you were calling dA for a small little chunk of area wasn't even an area. It was a point. It was dimensionless anyway. It had an infinitesimally small dx that way and an infinitesimally small dy that way. And this is a very important concept, because if you understand that this doesn't even exist, if you have a dx times a dy, like literally it's dimensionless and it don't exist, because there's a lot of proofs where you'll be going through numbers and you'll have like a dx and then a constant 1 plus, you know, constant 2 dx, and then you'll have, or dy, and then you'll have plus constant 3 dx dy. And guess what? Like, that's literally, it's less than 0, you know what I mean? And even these, you know what I mean, are 0 as well. Like, this is 0, but this is like hella more 0. So if you had p plus, you know, a constant dx plus a constant, if that was your equation, you know what I mean? Like literally, it's just like, hey, if it's like a shear force is just P or something like that for material mechanics. And yeah, it's kind of fascinating. But if you ever have an infinitesimally small thing multiplied by another infinitesimally small thing, and it's like saying 1 divided by infinity times 1 divided by infinity. You know what I mean? Like obviously that's hella 0, and this is hella 0. You know what I mean? Even more 0 than 0 could ever be. Alright, hell yeah. So that's kind of what I learned today is like even though you get this slice, you still don't have area. So it's just, well, it's dA prime. That's what we're doing. Alright, and then we're going to integrate that from 0 to t. So we're going to add all those slices 0 to t. So x is equal to 0 to x is equal to t. And we'll be integrating with dx. So if I have this dy, my limits of integration have to be in terms of y. And then if I have this dx, my limits have to go from x. You know what I mean? So, cool. And again, let's spell that out one more time. If I have this little chunk and I have this little dx, I can move it along the x-axis. That's how I would get this row of area. By taking this dx and then having a limit of integration from this value of x to that value of x. Same thing, I could have gone vertically. I would take this dy chunk and then move it from this value of y to that value of y. So those would be my limits on y, and this would be my little chunk I'm moving. And again, I'm getting a line. See, I'm getting the dimension of a line, nothing more. But it's kind of interesting to call it, oh, it looks like I got a little area. We're going to call that dA prime. And then we have to integrate again. So that's what we do. So the first integration, this becomes dy integrates to y. And so I'm going to have y evaluated at 0 to h, dx, and this is 0 to t. So, hell yeah, I'm going to have h. See where that came in? You know what I mean? Well, what did we say? This dA prime was just the dimension of a line. You know what I mean? It's just this. It has dimension. But look at this. Look, the units on this would just be units of inches. You know what I mean? If we're trying to get area, that's going to be inches times inches. You know what I mean? Or I got to get better. Well, I don't know. Like you could call it length times length. You know what I mean? Because there's only so many. You know, you have length, force, time, and mass. You know what I mean? There's only it's like the TFLT. I don't know, the engineering sandwich. Cool. And but yeah, base units. You know what I mean? Length is length, force is force, time is time, mass is mass. Yep. If you're, you know, yeah, like a moment. Like a moment is a force times a length. You know what I mean? So this is the smallest you can break these terms down into. Angular momentum is some mass. It's you know, kilograms out at distance, and you're squaring that distance. Because it's the leverage of distance. It's the leverage of this mass, but that distance squared. It's the second moment of mass. So moment of inertia is going to be mass length squared. Alright, hell yeah. Alright, booyah. So now that we have this h, and we got dx, and we have our limits from x is equal to 0 to x is equal to t, now we can integrate again. And essentially what we're doing is we're having that slice, which is a line that has a height of h, and then I'm adding all those little lines that have like no width, but if I add them up, you know what I mean? Hell yeah, I'll get that area right there. So yes, so we thoroughly took that little box dA, integrated it to get a line, and then we're going to integrate again to get that area. We could integrate into the plane or into the board. You know what I mean? If this thing had a three-dimensional shape. Sweet. Okay, so we integrate this. We don't have an x term, you know what I mean? Let's say this. Let's say this chunk, you know what I mean, just happened to go up at an x value of like y is equal to x, you know what I mean? So now this area is like that. Well, cool. So now I would have, you know, this line right there that I chose, well, You know what I mean? It could either be that height, or it could be this height, or it could be that height right there. So I wouldn't know. So therefore, like my limit of integration would be 0 up to, not a number, but the equation y is equal to x. So if I put y is equal to x here, we can kind of do that aside. I'm sorry. If this was the equation of this line, it has a y-intercept. This would be a slope of 1, but it would be y is equal to x plus h, because the equation of a line is y is equal to mx plus b. And that's why I'm doing this problem specifically, is because I swear, as an engineering student, seeing other engineering students, or maybe it was just me, I shouldn't, but I think a lot of students struggle with the most basic, is just like coming up with a very simple integration statement. You know what I mean? I think that's very difficult to do. Taking a line and then doing something with it with integration, especially flat lines. You know what I mean? I think it's even hard to see that this is an equation. If this is the origin, that this is a horizontal line which has an equation y is equal to h. And this even line right here can be important. It's y is equal to 0. And we could set an arbitrary, just like this. You know, this is an arbitrary xy origin. So I could put the origin down here, and this height could be some constant cy, and then this over here could be some distance cx. You know what I mean? And so then what would happen to the limits of integration? I would be integrating from a height of y would be cy, and then this value would be, the equation for this line would now be y is equal to x plus h plus cy. You know what I mean? And then what you would see is that this line right here that we want would be this equation. Well, I mean, after the integration, it spells it out, because after you integrate, you take the limits, and it's this upper bound, h, minus the lower bound. If your lower bound's 0, well, then you just get that height for that line. But if you started down here, you would have h plus cy, and then you would subtract cy. So that's how, and that's kind of the nature of integration. Is that anyway? Is that idea of, like, if you take a definite integral, like it's irrelevant where this thing is from the origin. You know what I mean? Or wherever you put your coordinate origin. All right, let's mosey on. So hell yeah. So we don't have, so when we integrate this, we don't have, this is the equation of that line, you know what I mean, but it's a constant. So when we integrate, we're just going to get xh. So let's do that. So we have hx, our limits of integration are 0 to t, and we're kind of done, you know what I mean. The area 1 is equal to this, it's ht. And does that make sense? The height is h, the width is t, and hell yeah, we're just money. Cool. So now we're going to do the same thing for this one, and then we'll do the same thing for A3. A3 is the only one that's going to be a little bit difficult, and then we'll be done with this video. So, alright, another little box. We're going to go dx, and then this is our A2. We have our dy. Now for this one, we started doing the vertical, you know what I mean? Well, let's do the opposite. Let's do the horizontal. So let's do the double integral. We're going to do that dx term. And so if this is our dx term, a distance x away, sorry if I said that wrong, because this is our dy term, a distance y away. We're going to do our limits of integration from here all the way to here. Now, what's the equation for that line? You know, think of them as lines. This is 0. Well, and does that make sense? Obviously, I'm just going to go from 0 to b. You know what I mean? You can just see that. But is that x is equal to 0 to x is equal to b? Well, what does x equals 0 mean? Right there. That's a point right there. You could say that's a point right at the origin. But how about up here? Is that x is equal to 0? Okay, sure. You know what I mean? It's still, like the y value has something, but hey, look at this. X is equal to 0, y is equal to h. You know what I mean? So this is still 0h. Cool. This is 0h minus t, if this thickness is t right here. Okay, hell yeah. But all these points, and that was kind of like the revelation today, is just like, I don't know. It's just like, sometimes it's easier to pick a point and be like, oh yeah, it's the same. It's 0, 0. X is always 0 along there. So let's go over here. This is going to be x is equal to b, y is equal to 0. How about right there? X is equal to b, y is equal to t. How about right here? X is equal to b, y is equal to h. Okay, so it seems like as long as I put a dot along this line, you know what I mean, the value of x is equal to b. So I can say, sure, this is a vertical line where x is equal to b. You know, it's no different than having the horizontal line. You know, right here, isn't y 0? Yeah, x is 0 is y 0. Over here, b is 0, but y is 0. So how about over here? You know what I mean? X is some value, but what's y? Is 0. So, hey, this is every point along this line, y is going to be 0. So this is an equation that explains the y term for every point along this line. And so we're just so familiar with the x being, the y being the vertical, the x being the horizontal, and you know, this is an equation y is equal to h. This is an equation y is equal to 0. Just instantly off the top of my head, I can see that we're saying that this is x equals b, and this equation is x equals 0. I have a harder time doing that, so that's why I just went over all that. Alright, booyah. So we're going to do this one the opposite way. We're going to do this dx first, and we're going to go from 0 to b. And now these aren't just numbers, even though it's the easiest one. Hey, this is an equation. This is x equals 0. You know, this could be x equals 2y. Like, what would that be? Yeah, that is harder to see. If this is the origin, and if I go over x, hey, guess what? I go up 2y. You know what I mean? So over 1 up 2. So maybe this line right here is this equation. You know what I mean? This would be x is equal to 2y. And does that make sense? Because let's flip it around. You know, all we have to do is divide by 2. Isn't this just y is equal to 1/2 x? Doesn't look like it, and it feels like I messed up. Yeah, I need to check my error on that. Yeah, my bad. That's why it's like, hey, if you have an equation, there was 2 ways I could have caught that error. I said when x was 1, y was 2. But just even saying that, 2 times 2 is 4, so that don't make sense. It would have been way better for me to say if y was 1, maybe I would have caught it. But 1 times 2 is 2. So when y is 1, x is 2. So this was the equation of that line. So even if we're integrating, like let's say this shape started from here, and then I was trying to find the area this way. You know what I mean? And I did a bad job because my limit of integration shouldn't have been 0. It should have been t. So sorry about that. Sorry. After all that, you know what I mean? The area of this is what we're trying to find. If we were trying to find the area of that, but we already found this. A1 was this whole thing right there. We're trying to find A2, and we got to start at the equation x equals to t. But still, now that we went over that, x equals t is a vertical line all along here. So, and that's the whole idea where we go to. Even our limits of integration, even if it is a constant, you can still treat it as a boundary line. It's a line, and that's important. And this is so fascinating. This line has to be, the units on the integration of this, has to be linear. You know what I mean? So whatever this value has to be in inches, or length to the first power, because after integrating, we are going to, or no, is that right at all? I don't think so. I think so. Yeah, it's just that this is that's tripping me out. Sure. Yep. And so let's keep tabs on this. All right, I think I kind of I don't know if I messed that up or not, because it has to do with whatever's here. If this was x dx, then these terms, and I was just trying to find area. If for whatever reason this, yeah, I don't know how I would explain that. These would have to be inverse of length or something to make that make sense. All right, let's not confuse ourselves. But we could have this line right here, and we could still be adding up this area. And so we would get this line, and we would say that this is, well, this is obviously y is equal to 1/2 x, and we just make this as x is equal to 2y, because we're going to we would start our limits of integration at x is equal to 2y, and we would go all the way to x is equal to b. And so now we can kind of start spitting out these these lines in terms of x. So even this one, we would still want it in terms of x. Alright, hell yeah. So now we can kind of move on. I'm going to rewrite this. So we have our first integral. Second integral, we have x is equal to t. We're starting at the thickness t. We're going to b. X is equal to b. That's going to be for our dx. Once we do that, we're going to get, from here to here, we're going to get that slice. Now that slice is a line, and it's a line that is in the x-axis. So if we tipped our axes, or just, you know what I mean? I mean, what you could honestly do, and let's do this in a second. It'd be kind of fascinating. I mean, just because as humans, we're just used to x, y. I mean, it's like reading a book. To make, and then we do the right-hand rule. And then so to make, yeah, how would you even do this? Yeah, you would do, if this is my, yeah, you just tilt it 90 degrees. So if I had the axis like this, and you probably wouldn't do it like that anyway, you would do it x, y, and you would have to invert it. See how you would just rotate it, but then you would have to invert it. So yeah, if you did this, you know what I mean? Hey, if this was the equation and this was 5, that would just be x equals 5. It might be easier to see. This would be x equals to y. You know what I mean? So, but yeah, that is tricky for the human brain, especially since we've, you know, do this a lot. X, y being in this coordinate system. Okay, so we have limits of integration on that first term. We get this line that's very much like flipping the axis. You know what I mean? Where you have x is in the, what is that called? The independent variable, and then the y is the dependent. And yeah, and then we're going to get something that looks like b minus t. So even right here is like in this direction. I mean, if we did flip our axes where we have x and y, what we're going to get is a chunk of area that looks like this, where this is our thickness t. This is t, this is b. And then so we get a line that's just like that. So that's the line that we get. You know, it's just kind of interesting looking at that. And then we're going to integrate that from y is equal to 0 to t. So this is going to be 0, this is going to be t, and it would be the same thing as this. And now you can even see that that thing's going to pop up where you're just like, oh, well, when I get the area of this, you know, I'm going to basically take the area of this whole area, and then I'm going to subtract this area. So this area gets subtracted, and then that gives me that final area. Okay, so we're going to integrate from 0 to t. But that's where this first integral covers that. And then so the y would be y is equal to 0, and then y is equal to t. And those are still equations. This is the equation of this line. It's y is equal to 0. The equation of this line is y is equal to t. Here's my dy on this element. I've already found the slice. The slice has a length of this length. It's not that length, because we're going to be b minus t, and you'll see that in a second. So let's do this integral. So we're going to have the y is going to be 0 to t. We're going to complete this integral, and we're going to get x whatever at these limits. And so let's do that. So we're going to have the integral of 0 to t. This becomes b minus t, evaluating these limits. That's what I was meaning to say, dy. Now, these equations are not functions of y, and some problems are, but hell yeah, these equations aren't functions of y. So when we integrate again, we just get b minus t y, and our limits of integration 0 to t. All right, hell yeah. So when we evaluate this, it's just going to be t gets inserted into y, and then we're going to subtract, should we spell that out? We have b minus t of t minus b minus t, and then you input the 0. So obviously this becomes 0, and this is that final evaluation. And what the hell was all this equal to? That was equal to that area. So the area 2 is equal to this. So area 2 is equal to bt minus t squared. And we did it. Alright, sweet. And keep that in mind, because at the end, what we're going to do is we're going to set b is equal to 10 inches, our height is equal to 10 inches, our thickness equals to 1, and so we're going to have 100 by 100 square inches minus this, which will be 8 by 9. And so that'll be 100 minus 72. That's kind of a good check on reality. This will have an area of 28. So that's a good way to check our equations. Okay, so yeah, that was good, because we did this one with reverse the limits of integration. You know what I mean? It was actually kind of, I don't know if it was harder to do it that way, but on this last one, should we try to do it again the hardest way? So we're going to have a little chunk of area. We're going to break down the dx. Go this way. We're going to have dy. We're going to have up to y. And then this way, we're going to have over. So I guess I should bring this all the way down. You know what I mean? So we have this dx, and we're going to have over to x. And on this one, we just need this area right here. So if I am going to do the x terms, it's going to be t to, it's going to be x equals to t, x equals to b. So you see that those are two equations of those lines. The equation of this line is y is equal to h minus t, and the equation for this line is y is equal to h. So doesn't really matter on this one which way to do it. Let's try to just do it both. So area is double integral dx dy. So if I do this dx term first, I'm going to move this little chunk from here to there. My limits are going to be x equals to t, x equals to b. And then after I do that, I'm going to get the equation for this line. And the equation for this line should be something, like the height of this line should be something like b minus t. You know what I mean? In that direction, hell yeah, that's the equation for that line is x equals b, is that right? Yeah, x equals b minus t. That's the equation of that line. Or just the height of that line. Just as if I had 5, and this was y is equal to 5, and I said, what's the height of that line? Well, I would say the height of that line is equal to this equation. You know, the height of that line is 5. For whatever reason, the height of this line is equal to that equation. Same thing in the x direction. The height of this line is x equals to b minus x equals t. So the height of this line is b minus t. Cool. Once I get the height of that line, then I can integrate, in this direction. If my origin is down here, I'm going to be integrating from this value of y to this value of y. So this value of y is b minus t to y is equal to b. And you can see that b minus t just becomes that thickness t. So I really didn't have to do this. You could change your axes and just say, hey, I'm just going to do this last integral from y is equal to 0 to y is equal to t. That's the same. I'm sure there's a way to like move your piece or change your axes. I don't know. I mean, it's kind of similar to the parallel axes theorem, but it's very simple when you're just doing area because it doesn't change the problem hardly at all. But it does, but the rules for integration and evaluating your limits, that b goes away. Because if I had if I had b and then b minus t and then just my y value here, and I y was equal to these two, this would just be b minus t, and this would be b minus b plus t, and then that would just be t. Cool. All right. So hell yeah. And I guess I said we was going to do this two ways. Might as well. So we got dy dx. So if I chose this as my little slice dy, I can move it in this direction. So I can make those little chunks go in this y direction. I can vary them in the y direction. And I would vary them from b minus t to b. So y is equal to b minus t, y is equal to, from b minus t to b. Cool. And then once I get that line, which has a height, if this was the equation and it was just y is equal to h, and my bad, this has to be h minus t. Yeah, in this direction, that's h. And I think I messed up here as well. Bummer. So the x direction is going to be b minus t. In the y direction, sorry, you probably caught that, is going to be, this is h minus t, and this is h for that height. My bad. So this would be, yep, all those would be h's. The h's cancel. Left with t. That's where I wouldn't have caught that mistake because the h is irrelevant because by integration it drops out. Okay, and so yeah, that gives me that value. The height of that line is just t. You know what I mean? Cool. And then we take that and we add those slices this way. So that's taking that dx. And what that means is like, hey, this height of this line is t. And then we have this value dx, which is infinitesimally small. But this still has a height, you know what I mean? So we take that height and this width, and then we just add up all those slices along these x terms. And we're going to do that from x equals t to x equals b. And so that's what we're going to do. Okay, so let's go back to up here. So we have dx along this. And we're going to integrate. We're going to keep our y terms. H minus t to h. Integrating this, we get x evaluated at b to t to b. And when we do evaluate this, we get b minus t, dy, h minus t, h. All right, and then these aren't, there's no y in here. These are just constants, and we can see that by the equations of those lines. Cool. And we're going to have, so integration, we get y evaluated, well, we have b minus t y evaluated at h minus t. Does that make sense? We're going to have h minus t to h. Okay, so this is going to be b minus t h minus b minus t h minus t. Looks like a lot will cancel because even this is bh minus th. This is going to be, oh, this is brutal. This is going to be, so we have bh minus bt minus ht plus t squared, and then we have a negative, so negative, positive, positive, negative. And we have a BH minus a BH, a TH plus a TH. And so we are just left with BT minus T squared. So that totally sucked, but whatever. And so that's our area. So area 3 is BT T squared. Let's see, had we had done it the other way, would it have been any easier? So we're going to have dy integrates to y, evaluated at h minus t. And I can just see that this is just going to be positive t, but let's spell it out. So we have dx, we still have those t to b. And so when we evaluate this, we're going to have h minus t. That's going to be h minus h plus t. That's just going to be t. So sweet. So now I have t dx, t to b. So obviously this one's going a lot easier. Integrating, we get tx evaluated t to b. Alright, ran out of juice, but hell yeah, when we evaluate these at the limits from t to b, we get tb minus t squared. Sweet, which is bt minus t squared. And that's what we get on the other one. So we did it twice. The third area is bt minus t squared. And now what we're going to do is I'm going to set some values on these. This is going to be 10 inches width, 10 inches height, just super simple, and then 1 inch around here. So if you took the whole area of that square, it's going to be 100 square inches. And then if this is 1 inch, it's going to be 1 inch here, 1 inch there. This would be a distance of 8. And then if this is 1 inch and this is 10 inches, this would be a distance of 9. 9 times 8 is 72. So we don't have 72 inches in the middle. If we took this full area minus this area, that's going to be 100 minus 72, which, oh, did I even get that? Yeah, it's 28. So, booyah. Alright, hell yeah. And I'm liking this because, check it out. Area 2 is BT minus T squared, and Area 3 was BT minus T squared. And this was Area 2, and this was Area 3. And so, you know what I mean, they should have been the same, and they were. This one was real simple. It was just h times t, so we see that. And yeah, so we should just be good to go. So let's plug these in. So the total area has got to be a1 plus a2 plus a3. And, our height is 10, so we're going to have 10. Our thickness is 1. Cool. And then area 2 is going to be, our base is 10, thickness is 1. Minus thickness is 1 squared. Alright, sweet. And then our base is 10. Thickness is 1 minus 1 squared. So it looks like we're going to have minus 2 at the end. You know what I mean? That's probably where we get that 28 from 30. So does this equal 30? Hell yeah. 10 plus 10 plus 10. So hell yeah. So we're going to have 10 plus 10 minus 1 plus 10 minus 1. That's going to be 30 minus 2. 28. So we have a nice little check on reality. But I think this problem is very good because it sets up vertical lines that have equations. This vertical line would be x equals to b. So I can totally see that. Vertical line, x equals to t. Just like I can spit out way faster that this line is y is equal to 0, y is equal to t, y is equal to h, y is equal to h minus t. Sweet. Alright, hell yeah. So I think we thoroughly did it. Thanks for joining me on this one. And guess what? That's a video.